what if we compare the signals in the frequency domain? Okay, then if it is slightly off, what frequency will this generate? 60 hertz. If we compare it to our stored frequency, what will it say? Is it a match or is it not a match? It's a match. Okay, exactly. So just like I'm saying, in the signals world, we have two choices. Compare things in the time domain or compare things in the frequency domain. Okay? Time is always problematic, but tiny bit of shift in time will make us recognize it incorrectly. But frequency has a lot more tolerance to it. Even if the data is shifted in time, as long as it's the same frequency, we'll recognize it correctly, right? Even if our measurement was off, let's say there's a little bit of a noise, and the frequency it recognized it was 59.5 instead of 60. Still, we can see, oh, it's very close to our recorded or stored data, so it must be, whatever is the very closest thing to it, right? Okay, exactly same way, once we go to the vision world or the image world, we have the equivalent of the time samples is pixels. Okay, so when we record a picture, whatever is the value of the red, green, blue is the pixel value. Okay, so if we compare things in the pixel domain, so in the image world or the vision world, okay, so if we did something in pixel domain, like a comparison in the pixel domain, will it be accurate most of the time or problematic? Problematic. Okay. So a lot of the techniques that I will show you will transform the pixels into some other domain. Okay. For example, one of the techniques that I was mentioning to you is principal component analysis, right? What it will do is it will transform the pixel domain to what we call the eigendomain. Okay, some of you probably took linear algebra before and would remember the concept of eigenvalues, eigenvectors. Even if you did not do it before, don't worry. I'll review it with you guys once I come to this topic. Explain what is the motivation behind it. How do we compute the eigenvalues, eigenvectors? So essentially, just to give you an overview today, let me give you an idea, just a tiny bit idea. Okay, so let's say I have some data point in 2 dimensions. So x-axis, y-axis, right? Okay, let's pretend I have a point. And this point is x of 4 and y of 3. So we can represent this data point as simply a number 4, 3. Right? The first part means the value on the x-axis. The second part means value on the y-axis, right? Okay, alternatively, in linear algebra, okay, we deal with matrices and vectors. What's the difference between two? Matrix is like a 2-dimensional data, like I showed you over here. So this is, for example, a 100 by 100 matrix as an example. Okay, a vector is basically an n. So a matrix could be m by n. This is the number of rows, number of columns. But or it could be a square matrix like n by n. A vector is always n by 1, meaning always a single column. Okay, so if you take a look at this example x and y, I could represent it as a vector as a single column with the value 4, 3. So what does 4 mean? The value on the x-axis. The second row is the data for the y-axis, right? Okay, what if I have a three-dimensional data? Okay, so what if I have a three-dimensional data? So let's say x, y, z, right? And let's say I have some point in space, and this point happens to be x of 3, y of 5, z of 2. Okay, can I represent it as a vector? So the vector will be what? 3, 5, 2. Okay, so if I gave you some vector, can you tell me how many dimensions are involved? So if I gave you some vector 4, 2, 9, 7. What dimensional space is it in? 4-dimensional space. And it's simply a point in the, for one data point, one point, just like this was a single point in 3-dimensional space, this was a single point in a 2-dimensional space, right? Okay, so now let's go to images. Okay, as I will show you, images are nothing but a single point in a very high dimensional space. Okay, so let's go to our picture of person X. Okay, we took the picture, this is the value of the red channel, value of the green. So we have 300 by 100 matrices, right? So now what we do is, okay, we convert, so this is a color picture, right? So this is a color picture. Okay, we convert it to grayscale. Okay, how do we convert it to grayscale? Okay, there's a weighted average that we take. There's a standard formula for it. Okay, so this. Okay, so grayscale value, okay, it goes something like this, 0.58 times the red value plus, I forgot, 0.31 times the green value plus I forgot, 11 something times the blue value. Okay, so my numbers are not 100% correct. I will give you the exact numbers in the next lecture, but it is close to these numbers. Okay, so if we multiply and to each one of the red, green, blue values, whatever that comes out, it will be a single number. Okay, so for example, if I do, let's say the last pixel, 0.587 times 95 plus 0.31 times 111 plus 0.11 times 197. Okay, it will produce some number. Let's pretend the number is 143. Okay, so once I do convert this to, right? So if I did this for every pixel, what will I get? I'll get a single 100 by 100 matrix, with some values, 241, 192. And let's pretend I convert it to the nearest integer. Okay, so this will be my grayscale data for the same color image. right? Okay, so let's say this was 87, let's say this was 92, 117, right? Okay, so now what I do is, even though this is a 100 by 100 matrix, I convert it to a vector. So how do I convert it to a vector? Okay, one possibility would be I go to each row and start writing it vertically, 241, then 192, then keep going. The last number in the first row is 87. Then I go to the second row, 92, and so on. And I keep putting all the data in the second row, all the data in the third row, all the data in the 100th row, and then whatever the last element is. And I assemble all of this data into a single vector. So my question to you guys is, what will be the size of this vector? See, how many numbers were over here? 10,000, right? So obviously this will be 10,000 by 1. So what does that mean? This person's picture is 1 point in what dimensional space? In 10,000 dimensional space, okay? So as you will see, when we do a transformation, we don't want to operate in the pixel domain, like as I showed you. That would be terrible. One shift of pixel will give us wrong recognition. So a lot of the computer vision, as you will see, is transforming this vector. So, which is again a data point in a high dimensional space. Okay, so sometimes we'll transform it to the eigendomain. Sometimes we'll transform to a certain nonlinear domain which cannot be mathematically described, but through deep neural networks, it will generate some kind of a compact representation. And then based on, so again, just to give you a tiny overview today, as to what kind of exciting things we'll be learning and doing. Okay, so one of the transformations that we will learn, as I mentioned, will be the principal component analysis, which will convert these to somehow to eigenvalues, eigenvectors, reduce the dimensionality so that a slight shift in the pixels does not cause a problem in the least square error. It still comes out very close. Okay, so there's a whole theory of it that we'll go through. Then you will write the code 100% yourself, even though there's a single line function available called PCA. See, that's my problem. I know some of you are in this course, some of you are also in the deep learning course. Okay, there are a lot of libraries available which will do all these complicated things with a single line of code. Okay, but then do you know how did it work? In my opinion, no. You're just treating it, oh yeah, something magical happened, but if you wanted to improve it, take it to the next level, this is where you need to understand the math behind it, the 100% programming behind it, so that you can now take it to the next level. Okay, so same thing. First, you will do 100% by yourself. And don't worry, I'll give you a lot of starting code. I know some of you are good in programming. Some of you may not be as good right now, but I guarantee you by the time you're done with this course, you'll be top-notch in this field, including Python programming, including C# programming, because you'll be developing fairly sophisticated applications, okay? And I'll provide, especially in the beginning, almost 80% of the code to you so that you go to that point, then slightly improve it. Gradually, I'll start to reduce what I provide to you so that in the last half of the course, I'm giving you maybe 20% starting code, then you are doing the rest, okay? Anyway, so 2 more minutes, then I'll let you go for today, and we'll start the actual detailed work next week. Okay, so to summarize, the way we will approach is, we'll start with basic image processing, how we manipulate images. Then we'll go to, as I say, filters with the theory. So there will be concepts like Taylor series involved, different partial derivatives involved. Again, don't worry even if you did not see it before. For first order derivatives, second order derivatives, so that you know how kernels are created rather than you going and looking up, oh yeah, I can use a kernel 1 to 1, minus 1, minus 1, minus 1, 1 to 1, apply it to the image and it enhances the edges. But where do these numbers come from? As I will show you, we need to go through the math and you'll see, oh wow, that's what it says it should be. This is how it should be done, right? Okay, then we'll take a look into, like, there are some very interesting algorithms like corner detection. There's like an algorithm called canny edge detection, very popular. So we need to understand, because you'll be using it quite a bit, how does it work, what's the theory behind it? Okay. Then, like I said, we'll go into object detection based on hard features. Okay, then we'll go into principal component analysis so that we transform this to eigendomain, and we'll start on the image recognition. So I'll try to finish all of these in the first half of the course, because these are classical techniques, okay? We want to spend more time on the latest, greatest things. Okay, the latest, greatest things are all based on deep neural networks. Okay, so there is a little bit of overlap in this course and the deep learning course that some of you are taking. Okay, but some of you are only in this course. So whatever component that we need from that course, I'll repeat it in a slightly different way so that you still benefit even if you were in the other class as well. Okay. So then over here, we'll take a look at object detection using YOLO. Okay. Then we will take a look at object recognition. Using what are called Siamese and triplet networks. And then some latest research. The great thing is about this particular course and also the deep learning course, everybody in the world is extremely excited about artificial intelligence. Okay? Artificial intelligence is being applied to computer vision. It's also being applied to, let's say, natural language processing, speech recognition, and so on. So in the deep learning, I'll be covering natural language processing aspect as well, whereas in this course, we'll strictly focus ourselves to vision. Okay, I'm very certain by the time we come to this part, there will be some latest research which further advances the state of the art. So whatever that is, literally like every month, there are 100 very exciting papers, at least 100, which are improving this field. So it's a very exciting time to be learning this field. Don't worry again about the math background. Any equations, concepts we need, I will clarify it so that it will come back to you very quickly. Any linear algebra concepts we need, I'll review it. Any programming that we run into, gradually I'll explain, give you the code, so that you also become better in programming as we go along, okay? So, one last thing. The course website Okay, I do not use Canvas, so do not send me any email or anything via Canvas. The course website is http://tv.bridgeport.edu, CPEG585, no spaces. The username is UB student. Okay, the password is UB student, lowercase, 2015, no spaces. Okay. Every lecture will be videotaped, and if you wanted to go back and review it, or for some reason you were not able to make it to the class, okay, you can always go to this website, download the lecture, replay it as many times as you feel like it. Any assignment that I give will be put on the website. And what I do is, I also put the lectures for last year are also there. In case you wanted to review something in advance, you can review it, come back over here. Of course, roughly speaking, in my opinion, maybe 60% of the course will stay the same as last year. A year is a long time in the artificial intelligence field, so 40% will change and cover the latest and greatest. Okay. Let's see, from programming point of view, if you at least this week can have Visual Studio 2017 installed. Okay, if you don't have it, come and see me. I will, through UB, have you install the proper, the professional version. Okay. Some of you have already done Python before. You don't have to use Visual Studio for Python. I prefer Visual Studio for Python as well. So a lot of the setup instructions and the code I'll provide will be based on Visual Studio. But if you're used to some other environment, PyCharm or something, I'm okay with it. You don't have to use it. But for C#, you don't have a choice. You have to use it. There's no other IDE for it. So at least have it ready so that you can see my code once I give you examples. Okay. Otherwise, enjoy this week. Hard work starts from next week. Okay. If you have any questions, let me know. Otherwise, I'll see you next week.
Great.